Hello everyone. Once again, welcome to this KTCHM e-learning channel. I am SK Marathe and this is my third lecture of T.Y.B.Sc Physics Paper First Mathematical Methods in Physics. In this lecture, we are going to discuss cylindrical coordinate surfaces and curves, and the transformation equation between cylindrical coordinates and Cartesian coordinates. Let us start. In first lecture, we have studied Cartesian coordinate system. As we have seen, Cartesian coordinate system uses three coordinates x, y, z to specify position of any point in three-dimensional space. And the Cartesian surfaces are the plane surfaces. The Cartesian curves are the straight lines, and the intersection of Cartesian surfaces, that is x surface, y surface, z surface, and the Cartesian coordinate lines, x line, y line, and z line, intersect at a single point. This we have seen. And the Cartesian coordinate system is applicable to physical systems having rectangular symmetry. In the second lecture, we have studied spherical polar coordinate system. As we have seen, spherical polar coordinate system use three coordinates r, theta, and phi to specify position of any point in space, where r is the distance of point from origin, theta is the angle made by this line OP with z-axis, and phi is the angle made by line OQ with x-axis, where OQ is projection of OP on xy plane. Then we have seen three coordinate surfaces, that r surface, then theta surface, and the phi surface. R surface is a spherical surface, theta surface is a conical surface, and phi surface is a half plane with one edge along z-axis. Then intersection of theta surface and phi surface is R curve. This line OP is R curve. Intersection of R surface and phi surface is theta curve. This red half circle is theta curve. Then intersection of R surface and theta surface is a phi curve. This red circle is a phi curve. This we have seen in second lecture. In this lecture, we are going to study cylindrical coordinate system. This cylindrical coordinate system use coordinates rho, phi, and z to specify position of point in space. And this cylindrical coordinate system is used in physical system. It is used to treat physical system which having spherical symmetry. For example, the electric field around a current carrying conductor. Or the another example is cylindrical capacitor. To describe such a physical system, this cylindrical coordinate system is used. This system use coordinate rho, phi, z. We have to define what is rho, what is phi, and what is z. Then take x, y, z as a reference coordinate system. Let us consider any point P. Its position is given by these three coordinate rho, phi, z. Then rho is a distance of point P from z-axis. That is this distance O dash P. Distance of point P from z-axis. That is O dash P is a rho coordinate. The value of rho is greater than 0. Is equal to 0 or greater than 0. If the point is on z-axis, then rho is 0. And as the point goes away from z-axis in any direction, in three-dimensional case, in any direction, then value of rho increases. This is first coordinate, rho coordinate. If we draw foot perpendicular from point P on xy plane, let it intersect at point Q on xy plane. then connect this line OQ, then angle made by this line OQ with x-axis is phi coordinate. This is same as in spherical polar coordinate system. That is, phi is the angle between line OQ and x-axis. That is, this angle XOQ is phi coordinate. This is also called azimuthal angle. And value of phi varies from 0 to 2 pi. It is in between 0 and 2 pi. This we have already discussed in previous lecture. If, if the point is in xz plane, then foot perpendicular is on x-axis, then value of pi is 0. And as the point goes away, then in this first quadrant, it is between 0 and 90. In second quadrant, 90 to 180. Third quadrant, 180 to 270, and fourth quadrant 270 to 360. This way pi varies from 0 to 2 pi. Then the third coordinate z. It is a distance of point P along z axis. Distance of point P along z axis, or it is a distance of point from xy plane. This is xy plane. From this xy plane, this distance of the point is z coordinate. Distance of point P from xy plane is z coordinate. In this figure, the distance PQ is z. The value of z varies from minus infinity to plus infinity. The point is below xy plane, then value of z is negative. The point is below xy plane, then value of z is negative. And if the point is above xy plane, then value of z is positive. In positive z direction, value of z is positive. In negative z direction, value of z is negative. In this way, the z varies from minus infinity plus infinity. This way, these three coordinate rho, pi, z. Rho is the distance of point from z axis. Phi is the angle made by line OQ with x-axis, and z is the distance of point from xy plane. Distance of point from xy plane. These three coordinates used to specify position of point in three-dimensional space in cylindrical coordinate system. Then the next topic, coordinate surfaces. We have already seen definition of coordinate surface. If one out of three coordinate, if one coordinate is held constant, out of three coordinate, if one coordinate is held constant and two coordinates allowed to vary, then we get the coordinate surfaces. In cylindrical coordinate, the first surface is a rho constant surface. Rho constant surface. It is rho constant surface if rho coordinate is held constant. Rho coordinate is held constant and phi and z allowed to vary. Then we get a surface of cylinder. Therefore, rho constant represents surface of a cylinder with its axis. Axis of the cylinder is along z axis. With its axis along z axis, and the radius of cylinder is rho. Radius of cylinder is distance of point P from z axis. That radius of the cylinder is rho. All points on this surface have same value of rho coordinate, but value of phi and z coordinate vary from point to point. That is, if we connect all points which are at a distance rho from z axis, then we get a surface, and that surface is cylindrical surface, and that cylindrical surface is rho constant surface. This is the first coordinate surface, rho. Let us discuss second surface, that is phi constant surface. This phi constant surface represents the half plane with its one edge along z axis. This we have already discussed in spherical polar coordinate system. This is same in this cylindrical coordinate system. This green color half plane with its one edge along z axis represents the phi surface, because if we draw foot perpendicular from any point on this surface, then it intersect on line OQ. Therefore, the angle phi remains same for all points on this surface. Therefore, this is phi constant surface. All points on this surface have same value of phi. Phi is constant for all points, but value of rho and z coordinate varies from point to point. As we go along z axis on this plane, value of z increases. As you go away from z axis, value of rho increases, but value of phi remains constant. Therefore, this is phi constant surface. Then the third surface is a z constant surface. Z constant surface is a plane surface which is perpendicular to z axis. The z constant surface is perpendicular to z axis and it is parallel to xy plane. This is parallel to xy plane. It's xy plane, and this z plane is parallel to xy plane, and the distance of this plane from xy plane is z. That is all points on this plane. If we consider any point on this plane, then it is at a distance z from xy plane. Is at same distance z. Therefore, z is constant for all points. But value of rho and value of phi varies from point to point. As we go away from z-axis, value of rho increases. Then the foot perpendicular is in different quadrants for different points at different position. Therefore, phi also varies. For phi changes, rho changes, but z is constant on this plane. Therefore, this surface is z constant surface. All points on this surface, same value of z coordinate, but value of rho and phi coordinate is from point to point. This way, three surfaces. On rho surface, rho is constant. On phi surface, phi coordinate is constant. And on z surface, z coordinate is constant. And next topic, coordinate curves. The intersection of this definition of coordinate curves we have already seen that intersection of two surfaces gives a coordinate curve. Intersection of two coordinate surfaces gives a coordinate curve. Let us see three curves. The first one is a rho curve. This rho curve is intersection of phi. Phi, that is this half plane. Phi surface is a half plane. And z, z constant surface, that is this plane perpendicular to z axis. Then intersection of the z constant surface and phi constant surface is this line O dash P, red line. O dash P is the intersection of the surface S2 and S3. If we observe this line O dash P, then along this O dash P line, only rho, value of rho varies from point to point. As we go away from z axis, value of rho increases. But all points on this O dash P line are at a distance z from xy plane. All points on this O dash P line are at a distance z from xy plane. Therefore, z is constant. The foot perpendicular from any point on this line O dash P is on this line OQ. Therefore, phi remains constant. For all points on this line O dash P, phi is constant, z is constant, only rho varies from point to point. Therefore, this is rho curve. Then the second curve is a phi curve. Phi curve is the intersection of rho curve and z curve. Rho curve is a cylinder. This S1 is a cylindrical surface. And z curve is this plane perpendicular to z axis. Intersection of this cylinder and plane is this circle, this red circle. This red circle is phi curve. If we observe this red circle, then along this red circle, value of phi varies from point to point. But value of z is constant and value of rho is constant because all points on this circle are at a distance rho from z axis. All points on this circle are at a distance rho from z axis. Therefore, rho constant. And all points on this surface circle are at a distance z from xy plane. All points on this circle are at a distance z from xy plane. So rho constant, z constant. But phi varies from point to point. If we consider points in this quarter, then foot perpendicular is in first quadrant. Therefore, value of for these for points which are in this quarter, the value of phi is from 0 to 90. For this quarter, 0 to 180. For this quarter, 180 to 270, and for this 270 to 360. In this way, value of phi varies from 0 to 360. But rho is constant, z is constant. Therefore, this is phi curve. Then the third curve is a z curve. Z curve is the intersection of rho surface, that is cylindrical surface, and phi surface, that is half plane. Then this cylinder and this half plane intersect along line PQ. The cylinder and the half plane intersect along line PQ. If we observe this line PQ, then all points on this line PQ are at a distance rho from z axis, at a distance rho from z axis. Therefore z constant, rho constant. All points on this line PQ are at a distance rho from z axis. Therefore rho is constant, and foot perpendicular from any point on this line is at point Q. Therefore phi is also constant. Only z varies from point to point. At point Q, value of z is 0. As we go above along z axis, value of z increases. From Q to P, value of z increases. This way, value of z varies from point to point. Rho is constant, phi is constant. This is z curve. This way, we have seen three curves: rho curve, phi curve, and z curve. And these three surfaces, that rho surface, phi surface, and z surface, and three curves, that rho curve, phi curve, and z curve, intersect at a single point, that is S1 surface, S2 surface, and S3 surface. These three surfaces intersect at point P, as well as the three curves, that is this O dash P is a rho curve, this circle is a phi curve, and this PQ is a z curve. These three curves also intersect at a point P. Then unit vectors. The first unit vector E rho cap. This unit vector E rho. This unit vector E rho is normal to cylindrical surface, rho surface. This is normal to cylindrical surface. At a point P, this E rho is perpendicular to the cylindrical surface, and its direction is along the increasing direction of rho. Value of rho increases from O dash towards, therefore direction of this unit vector is along the increasing direction of the rho coordinate, and it is perpendicular to the rho surface. Then second unit vector is E phi. This second E phi cap. This E phi cap unit vector is normal to phi surface. This half plane is a phi surface, and normal to this half plane is E phi, and its direction is along the increasing direction of phi. This is the increasing direction of the phi. Therefore, direction of this E phi cap unit vector is along the increasing direction of phi. Then the third unit vector is Ez cap. This Ez cap is normal to the Z surface, to this S3 surface at a point P. This is Ez cap, normal perpendicular to the Z surface, and its direction is along the increasing direction of Z. This is the increasing direction of the Z coordinate. Therefore, the direction of unit vector is along the increasing direction of the Z coordinate. And these three unit vectors are perpendicular at a point. They are mutually perpendicular at a point. Their direction varies from point to point, but at particular point, they are perpendicular to each other. Next topic, transformation equations between rho phi z, that is cylindrical coordinate, and xyz, that is Cartesian coordinate system. That is transformation equation between cylindrical coordinates and Cartesian coordinate. Let us first derive the relation between Cartesian coordinate in terms of cylindrical coordinate. Let us derive Cartesian coordinates in terms of cylindrical coordinates. Let us revise this figure again. For point P, in Cartesian coordinate system, the coordinates are x, y, z. In cylindrical coordinate system, the coordinates are rho, phi, z. X is the distance along x-axis, y is the distance of point along y-axis, and z is the distance of point along z-axis. Just we have seen rho is the distance of point from z-axis, phi is the angle made by line OQ with x-axis, and z is the distance of point P along z-axis. That is, z coordinate is same in Cartesian coordinate system and cylindrical coordinate system. This distance O dash P is rho. This distance O dash P is rho. Therefore, this OQ is also rho. This distance OQ from the geometry of the figure, this rho. Therefore, this is rho. Then from triangle ONQ, this right angle triangle ONQ, this angle is 90 degree. This angle is 90 degree. From this triangle ONQ, cos phi is equal to adjacent side ON upon hypotenuse OQ. Cos phi is equal to ON upon OQ. But ON is x. This ON is nothing but x, and OQ is rho. Substitute ON is x and OQ rho. Then we get x is equal to rho cos phi. This is the first equation. X is equal to rho cos phi. Again, from the same triangle, sin phi is equal to front side upon hypotenuse. Front side is NQ. Front side is NQ, which is y. And hypotenuse is OQ, which is rho. OQ is equal to rho. Therefore, sin phi is equal to y upon rho. Therefore, y is equal to rho sin phi. Second equation, y is equal to rho sin phi. And z is same in Cartesian coordinates and in cylindrical coordinates. So we get three equations. X is equal to rho cos phi, that is Cartesian coordinate x in terms of cylindrical coordinate rho and phi. Y is equal to rho sin phi, that is second Cartesian coordinate in terms of cylindrical coordinate. So three equation, x is equal to rho cos phi, y is equal to rho sin phi, and z is same. Then let us derive cylindrical coordinates in terms of Cartesian coordinate. That is, obtain rho phi z in terms of x, y, z. Just we have derived x is equal to rho cos phi, y is equal to rho sin phi, and z is equal to z. Then if we solve this equation, x square is equal to y square. Substitute x is equal to rho cos phi, y is equal to rho sin phi. Then we get rho square cos square phi plus rho square sin square phi. Take rho square common from this equation. Then rho square in bracket cos square phi plus sin square phi. But cos square phi plus sin square phi is equal to 1. Therefore, we get rho square is equal to x square plus y square. Therefore, rho is equal to square root of x square plus y square. This is rho in terms of xy. Then obtain this ratio y upon x. Solve this ratio y upon x. That y is equal to rho sin phi and x is rho cos phi. Then substitute rho sin phi upon rho cos phi. The rho get cancelled. Sin phi upon cos phi is tan phi. Therefore, phi is equal to tan inverse of y upon x. This is the second coordinate, phi in terms of xy. Phi is equal to tan inverse y upon x. And z is as it is. This way, these three equation, rho is equal to square root of x square plus y square. I is equal to tan inverse y upon x, and z is equal to z. These are the cylindrical coordinates in terms of Cartesian coordinates. In this way, in previous lecture, we have obtained Cartesian coordinate in terms of spherical or polar coordinate, that x, y, z in terms of r, theta, phi. These are the equations. Then spherical or polar coordinates in terms of Cartesian coordinates, that is r, theta, phi in terms of x, y, z. In this lecture, we have derived the Cartesian coordinate x, y, z in terms of rho phi z, that x is equal to rho cos phi, y is equal to rho sin phi, z is equal to z. and cylindrical coordinates in terms of Cartesian, that rho phi z in terms of x, y, z. This, these are the important equations which we require for in next lectures. That's all in this lecture. Thank you.